Okay, so I refreshed my memory about that thing I did not derive, so I will derive that, and then we will start with the entropy inequality. So I think what I was trying to show you was that SLM E dot LM is same thing as TIL tilde F dot IL. I think that's what I was trying to show you. And the relationship between TIL and S is FIL SLM equals T tilde IM. So it's T tilde equal to Fs. So my guess was right. So I'm going to start with this. So SLM E LM is FIL FIM minus delta LM over 2. So if we differentiate that, so let's say E dot LM equals SLM 1 over 2 F dot IL FIM plus FIL F dot IM. Right? Chain rule of calculus there. So if we now look at this term, so we have SLM FIM F dot IL. So that's the first one. And the second one is 1/2 FIL SLM F dot IM. This time I put this in between because this thing is T tilde. And here S is symmetric. So I can write SLM as SML. S is symmetric. So I get 1/2 FIM SML F dot IL plus that term. There is a 1/2 here. So this thing is also T tilde IL. So that SLM E dot LM equals this. You need this in if you are writing a finite element code, then you need this. That S dotted with E dot equals T dotted with F dot. Even when you are writing when you are using variational principle or you are driving a weak formulation of the problem. So in the weak formulation of the problem, you will say T IL delta FIL. So this is the variation of the deformation gradient. So this thing will equal SLM variation of ELM. Which is the same thing. I am replacing dots F dot by the variation part. So you, if any one of you has worked in say rubber elasticity or nonlinear elasticity and try to drive a weak formulation for finite element for writing a finite element code, you will need this. I think some of you asked me about one carbon nonlinearity. So if one carbon nonlinearity, if one carbon nonlinear strain is not quite ELM, actually it is not, because you neglect some quadratic terms in the displacement gradients. So therefore this equality does not strictly hold, and there is no stress tensor that is work conjugate of one carbon strain tensor. You can make approximations, that's fine. I mean, it's okay. Some people do it knowingly and some people do it not knowingly because they don't know it. So if you do it knowingly, then you know that you have introduced an approximation, and numerical solution is an approximate solution, but the problem is if we make ad hoc assumptions, then we cannot say the solutions should converge or must converge as you refine the mesh. Refining the mesh is equivalent to using more terms in the Fourier series of a function, Fourier series expansion of a function. So you expect that as you increase the number of terms in the Fourier series, the error in your approximation should decrease. Same thing should happen in the finite element work. For linear problems, one can derive estimates, one can find the error estimates, and one can show the rate of convergence, like how if you decrease the element size, how fast should the solution converge. But for nonlinear problems, there are no results known. Okay, so I think in the morning I gave up too soon because I should have just kept on going and switched this around. Is it okay? So let's rewrite the entropy inequality we had. So we had rho 0, I think phi dot plus eta theta dot minus TIL F dot IL plus QL GL over theta less than or equal to 0. Please check if my recollection is okay. And we said we will define thermoelastic materials. So we have now basically a bucket of materials. So these materials have the property that all of these constitutive variables, they depend upon F, theta and G, where GL is the temperature gradient. I did not put indices here, but anyway there are indices here, right? So phi, T, eta, energy and Q, all of these depend upon the present values of the deformation gradient, present value of the temperature and present value of the temperature gradient. So for us a thermoelastic material is one for which these constitutive quantities at the material point X depend upon the values of these variables at that point X. So this is a local theory. It does not say that the value of phi depends upon F at all points in the neighborhood of X. It only if you do that, then you get a non-local theory. The balance laws don't change. The balance laws we wrote, like this morning, all of them, including the entropy inequality, stay the same. If you say I want to study non-local theory, then you will say value of phi at the point x at time t depends upon phi not only at the point f, but f in the neighborhood of x. And now it will depend upon how large or small a neighborhood you take. So in the gradient theory, you take a very tiny neighborhood. Tiny means all you really do is, instead of f, I think when I was expanding in terms of Taylor series, then I said you keep the second order term. So you take f is, so you take the derivative of f, fil. So you say, okay, it will depend upon not only f, but also the gradient of f. Then the question is, why not gradient of g? See, if I say it depends upon theta and the gradient of theta, that's what g is, right? This g. Then why don't I say gradient of g? I mean, why should we treat temperature, second order derivative of temperature differently from the second order derivative of motion? Actually, I did that. I did consider second order derivatives of g. This is like 40 years ago. And in that case, you do get finite speeds of thermal waves or thermal disturbances. So it is possible you get a, but problem again becomes you have more constants. How do you find them? So as more sugar you put in your coffee, the sweeter it gets. So it's the same thing here. The more gradients you consider, hopefully you are getting better results. But the putting sugar is a lot easier, whereas in this case finding values of material parameters is much harder. So we are going to stay with the classical stuff. Local theories. So if I do that, now let's phi is a function of all those variables. So I'm going to differentiate them and use the chain rule of calculus. So it's delta phi over delta f I l f dot I l plus delta phi over delta theta theta dot plus delta phi over delta gl dot plus eta theta dot minus t I l f dot I l plus 1 over theta q l gl is less than or equal to 0. Right? I mean, we did not do anything except we rewrote that and substituted for phi here. Now we are going to combine the terms that have theta dot and that have f dot. So if I rewrite it, so I have rho 0 delta phi over delta f I l minus t I l tilde f dot I l plus rho 0 delta phi over delta theta plus eta theta dot plus delta phi over delta gl dot plus 1 over theta ql gl is less than or equal to 0. So for a thermoelastic material with this being the definition of a thermoelastic material, the entropy inequality or the reduced entropy inequality is this one. So it must be satisfied for all solutions of the governing equations. So what I said in the morning was that only those solutions of the governing equations are admissible that satisfy this equation. Okay. Now in the governing equations, we have rho j equal to rho 0, but j is determinant of f. The next one is rho 0 ui double dot. We had the gradient of TIL XL, so this will be say FJM over XL plus IL over theta over XL. You don't need to write this, but I do to give you my reasoning, and plus rho 0 BI, and same thing for the energy equation, which I won't write. Now I purposely wrote it, you don't need to write it because I need to make a point, and I did not write the next one. Is similar reasoning. Okay, so the reasoning is something like this. What we are looking for is U, displacements, which satisfy these governing equations. So if in these equations, supposing I have a solution, say f, theta and g. F is a deformation gradient. I put tildes because these are 9 components. Temperature is scalar, 3 components of g. So we have 13 quantities. So if supposing I choose these 13 quantities, f, theta and g, I can find body force in principle. I can find body force so that this equation is satisfied. So here the argument is, this is not my argument, this is the argument due to Coleman and Knoll. Due to Coleman, C-O-L-E-M-A-N, Coleman and Knoll, they said, or they argued, that these body forces are, all kinds of body forces are available to us. Whatever we need, we can produce. So you assume f, theta and g, anything you like, so long as they are differentiable. You substitute in this, you can find the body force, so it is satisfied. Same thing for the energy equation. Energy equation, we had rho 0 R term, that radiation term. So you can find R, so that energy equation is satisfied. The counter argument is, some people have done that. Ingo Muller say. Ingo Muller, he argued that we do not have all kinds of body forces and sources of internal energy available to us. And we are going to consider only those bodies which are insulated from the environment. So the body force is 0 and the radiation term is 0. And then you can regard this as a constraint equation, Lagrange multiplier. Energy equation as a constraint equation, use Lagrange multiplier. And then say, okay, this entropy inequality holds under these constraints. That reasoning also gives you the same result as what we are going to get. Okay. Other people, like say Green and Lindsay, they argued that, see here we took entropy flux as heat flux over temperature. They said we don't know that, which is fine, yeah, which is true. They did not want to make that assumption. So they said, okay, we are going to take entropy flux as a constitutive variable. And then you can, again you find restrictions of the kind I am going to show you in a minute now. So there are different viewpoints. For these simple materials, simple in the sense there is no memory effect involved here. There is no polarization involved here. So for these kind of materials, all these different approaches give you the same answer. But if you take a more quote unquote complex material, then you may get a different answer. So this is one approach, not the approach. There is a difference between a approach and the approach. A is one of several possibilities. I did not know that the use of these articles A and the when I was your age. So A is one of the several approaches. It is being non-specific. D is there is only one, or you are specifying which one. So here we are using Coleman and Knowles approach, which is one of the several approaches possible to use or to express the second law of thermodynamics in an equation form. So please don't get the impression that this is the way to do the problem. This is one of the several ways to use second law of thermodynamics. Okay, so now the argument is like this. So if you give, I choose any f, theta and g, these values of these 13 variables, I plug them in here, I find b and I find r, so these equations are satisfied. So I don't have to worry about the constraint part. However, when I choose f, theta and g, there is nowhere I have to choose f dot or theta dot or g dot, right? I did not say you choose f dot, theta dot, g dot. So f dot is arbitrary, theta dot is arbitrary, and g dot is arbitrary. And this inequality, the left hand side of the inequality, has a polynomial of degree 1 in f dot, theta dot, and g dot. There is no f dot does not appear here, it does not appear here. Look at the assumptions. There is no f dot in this one, no theta dot, no g dot. Same thing here, same thing here, right? I mean, there is no f dot here, but in all this term g dot is multiplying something which I can change by changing f, theta and g. Theta dot is multiplying something I can change by changing f, theta and g, and same thing here. So this is the argument I am trying to make now. So I have this a x plus b is less than or equal to 0, where I can change x any way I like. So what condition must be on A for this inequality to hold? Yes? Equal 0. Very good. See, if it is not 0, I can choose x so that this inequality is violated. Does it make sense? So that is the argument. The argument is that given f, theta and g, I can find the body force and the source of internal energy so that my governing equations are satisfied. And now for the entropy inequality to be satisfied, I must have this term equal to 0, this term equal to 0, and this term equal to 0. So if you agree with that, then so we get TIL tilde equal to rho 0 delta phi over delta FIL, and eta equal to minus delta phi over delta theta, and delta phi over delta GL must be 0. See, in the morning we were saying some authors or some people assume free energy does not depend upon temperature gradient. But now we are proving it, that the entropy inequality requires that the Helmholtz free energy must not depend upon temperature gradient. The argument, I think, as I said before, it is Ax plus B must be less than or equal to 0. So if then what is left is QL GL 1 over theta must be less than or equal to 0. So the entropy inequality requires, or the Clausius-Duhem inequality requires, that the Helmholtz free energy must not depend upon temperature gradient. Furthermore, the first Piola-Kirchhoff stress tensor must be obtained from the Helmholtz free energy by differentiating with respect to F. Entropy equals derivative of phi with respect to temperature. See how much our problem has been simplified. We had to find 1, 2, 3, 4, 5. Well, this was actually we had to find 1 plus 9, 10, 11, 12, and 3, 14 functions for a thermoelastic material. That's what we define by thermoelastic material is one for which all of these quantities depend upon the present values of F, theta, and G. What the entropy inequality gives you, or the second law of thermodynamics gives you, is that these 9 quantities can be derived from the free energy phi. Entropy can be derived from phi. Furthermore, phi cannot depend upon GL. So if you know phi, if I know this, I don't have to worry about these two. So I get the remaining 10 free, or 9 plus 1, 10 free. See the simplification caused by the requirement that entropy inequality must be satisfied. And once we do that, say once I find TIL and eta from these, I don't have to worry satisfying the second law of thermodynamics. It's satisfied. So that's what happens. See, when you don't see in books that the second law of thermodynamics even mentioned, that's because they have found, first of all, they have taken phi to be independent of the temperature gradient. So this is satisfied. And if they are doing a mechanical problem, they have found T from this relationship. And then they, of course, in the mechanical problem, you are not worried about entropy. So once you find, you make this, or you satisfy this and these, you are done. So second law of thermodynamics is satisfied. And that's one reason you don't see mentioned anywhere that our solution must satisfy the second law of thermodynamics. Okay. I mean, we are not home yet, because for a thermoelastic material I still have to find phi, and I still have to find q, the heat flux. And if I know eta entropy from this, then finding E is no big deal, because we said phi equal to E minus eta theta. Therefore, E is phi plus theta eta, which is minus so not only we get these three, we get this one also. So the problem basically reduces to finding phi and finding q, heat flux. Please speak up if you have any question now. Well, this is basic. Unless you believe this, doing viscoelastic materials is not going to be any fun.
So can we say that Coleman and Knoll inequality principle kind of places a more restrictive thing on the principle of equipresence?
No. Trussell gave the principle of equal presence before Coleman and Knoll used the entropy inequality. Okay. The thing that Trussell did not exploit or did not state is how to exploit the entropy inequality to get restrictions, that's the word you use, on the constitutive quantities.
Right, but Trussell is saying that the principle of equipresence requires that these variables that we have chosen to define to represent the thermoelastic material,
right,
should depend on all these three
yes.
theta g. But now we are finding that.
Wait. Sorry. There is a statement after that too. Trussell's principle of equipresence states that a priori we must not assume any specific dependence or exclude any variables. Okay. So the principle of equipresence states that to start with we must assume that phi, T, eta, E and heat flux, all of them depend upon the same variables unless the second law of thermodynamics rules them out. So a priori we did not assume that. Okay. So a priori we are saying all of them are being treated equally, that's what we did. However, entropy inequality says that your assumption of treating them equally is not a great one, is not appropriate to satisfy the second law of thermodynamics. So this is second law of thermodynamics that is ruling it out. That's ruling out that phi depends upon g. It says no, it cannot depend upon g. T cannot depend upon g. Eta, no, cannot depend upon g. E cannot depend upon g. So it verifies, I mean, if I can use that word, whatever people before Coleman and Knoll had been assuming. So it verifies basically what people had been assuming. And I cannot say that it proves that, because see, unless we make assumptions you don't get anything. If those of you who study math, you see that let this be true, then this holds. That's what we are doing. So when they say let this be true, it's the same thing we are saying, we assume this. So it's the same thing saying that let this be true is the same equivalent to saying let's assume this. So if this holds, then this holds. So that if this holds means if this assumption holds, then this is the consequence. So the consequences of all of these our assumptions like these we make here, we get results, and if we do experiments and predictions from this theory do not agree with experiments for all kinds of loadings, not one loading. If I can find one loading for which predictions don't agree with the theory, with the experiment data, theory is bogus. As counterexample, I just only need one. But saying that the theory is valid, I need lots and lots of example problems. But that's way, fortunately for us, predictions from these so far have been shown to be good, have been shown to be valid. So we are happy. Otherwise, somebody would have shot me by now, or because why are you teaching us garbage? So the predictions, like you were somebody was asking me about elasticity. I mean, linear elasticity is a subset of this, and things work beautifully. I mean, you design something based on linear elasticity, within the limits for which it is designed, it works very well. So these things, I mean, fortunately for us, things work very well, even for large deformation based on this theory. We are not done yet because we still have to find this phi. Okay, so now let's see what this one gives. This is, oh, I forgot here, QL GL is less than or equal to 0. So I will first work with this, and then we will see how can we simplify phi further so that we have to do fewer number of experiments. See, at this stage of the game, all we have said is phi cannot depend upon G, so really phi is a function of 9 plus 1, 10 variables, 9f, deformation gradient, and temperature. So this is a function of 10 variables. Now let's see if we can make it a function of fewer than 10 variables. Okay, so that's the next thing. What the exact function we cannot find theoretically. I mean, we can go so far theoretically, then eventually we have to do experiments. Like finding Young's modulus, either you do molecular mechanics simulations or you do physical experiments. Molecular mechanics simulation, those of you who are doing, they are based on molecular mechanics potential. So the value of Young's modulus you will get will depend upon what potential you are using. And if your potential is wrong, then your rest of the work will be wrong. So we are back to square one. How do you get the molecular mechanics potential, which is the same thing as getting, how do I get this phi? It's the same problem. Okay. Molecular mechanics potential, you say, okay, I will rely on density functional theory. Solving that Schrodinger equation is not easy. So it's really no free lunch. I mean, you still have to do a lot of work to get that MD potential, molecular dynamics potential, and we have to do a lot of work to get this phi. So we will focus on getting our phi and let other people, actually I really don't know anything about density functional theory, so I even cannot say anything more. I just have heard the word density functional theory and Schrodinger equations that we have to solve those. But how do we get Schrodinger equation from density functional theory, or what kind of assumptions we make, I have no idea. So, okay, I have some idea about this, so let's do that. Now let's look at this one. You will be happy to see some consequence of this. When I say happy, because you are familiar with those. Most of you are familiar with those. First of all, theta is positive, so I don't have to worry about it. Because I can multiply both sides by theta and still this thing should hold. Now, if I call, say, alpha equal to QL GL, so alpha is a scalar and it is less than or equal to 0. So when does the value of, so value of the maximum value of alpha is 0, and that maximum value occurs when GL is 0. Because if I set GL equal to 0, I get alpha equal to 0. So first thing is derivative of this with respect to the deformation, with respect to the temperature gradient, which is now delta QL over delta GM GL plus QL delta LM should be less than or equal to 0. Oh, not this thing evaluated at G equal to 0, which means this thing evaluated at G equal to 0 should be 0. That follows from this, because alpha has a maximum value when G is 0. So that means its first derivative should be 0 when G is 0. And if you set G equal to 0, this term will go away. So what we are getting here is that Q of M, heat flux, no matter what F is, what theta is, and if G is 0, then this is 0. So no temperature gradient, no heat flux. It's good. That's what Fourier law said. If in the absence of temperature gradient, there is no heat flux. I mean, this we are getting from entropy inequality rather than making an assumption. So what can we say about the second derivative? Because if alpha is positive, sorry, alpha is maximum when G1, G2, G3 are zeros. So what can we say about the second derivative? So the second derivative, I need to keep this stuff. So the second derivative of alpha, which is right, delta alpha square over delta Gm Gn evaluated at G equal to 0. So what should be that? It's a now 3 by 3 matrix. Should it be positive definite or negative definite? Negative definite. So this is a sign for negative definite. It doesn't mean less than or equal to 0. So this is maybe I should not write like that. So it's negative definite. And I think if you want to see how it is, you can look at the Taylor series expansion. So that's f of x plus h f prime of x plus h square over 2 f double prime of x. So if f of x if f is maximum at h equal to 0, if f is maximum at h equal to 0, this term we are saying is 0 because we set first derivative equal to 0. So if this thing is greater than that, then this quantity must be negative, right? So that's what that means. It's negative definite. This this minus sign means negative. I didn't. Oh, wait. It's not dash. So it's negative definite. I'm still lazy. I did not write NEGA one. I think I know how to spell that, but I'm lazy. So it's negative definite. So let's differentiate it. So if we do that, so we differentiated once here. So let's differentiate this again. So if we differentiate it again, so we will get QL over GM GN GL plus delta QL over delta GM delta LN plus delta QM over delta GON, all of this evaluated at G equal to 0. Right, put G at the wrong location. All of this evaluated at G equal to 0 is negative definite. So now we are getting somewhere. So what will happen? When we set G equal to 0, this term will go away. So this one is delta QL over delta GM, but L and L this, so it really becomes N plus delta QM over delta GN G equal to 0 is negative definite. And what is the derivative of heat flux with respect to temperature gradient? So that's called thermal conductivity. So in our case, no, it's a thermal conductivity tensor because it has two indices, N and M. It has two indices. So it's not a scalar like we are used to thinking, because we did not say anything about the material, whether it is isotropic or not. I think some of you are, any questions about this and yourself? Is it okay? So we did not say anything about the material symmetry yet. So this is a conductivity tensor. What it says is the symmetric part of the conductivity tensor. It doesn't say anything about the skew symmetric part of the conductivity tensor. So symmetric part of the conductivity tensor evaluated at temperature gradient equal to 0 must be negative definite. And generally the negative of this quantity is called conductivity tensor. So that will mean conductivity tensor must be positive definite, because conductivity tensor normally is defined as negative of the heat flux with respect to temperature gradient. So the symmetric part of the conductivity tensor must be positive definite or positive semi-definite. It doesn't say strictly, it doesn't say greater than 0, it just says less than or equal to 0. So see, we got results which we are familiar with, that conductivity tensor should be positive or conductivity should be positive as a consequence of the entropy inequality. We did not assume that. Okay, now I'm doing good on time. So we can have a break and then we will talk about how further we can simplify phi. Remember, it's now a function of 9 plus 110 variables. So we are going to use some arguments which are realistic, okay, which are meaningful. I'm not going to pull anything out of here, and see instead of having 10, can we make it little less? And then we will be stuck, because we will have to do experiments. Okay, so let's have coffee and then or tea, and then we will pick it up.
Is it possible to have a material where the heat flux is nonlinear and independent?
But if we start at 410, then we will be done at 5, and we will not keep them longer. Any question you want to ask before we go further? So what we are going to do is thought experiments, no physical experiment. So next thing will come up in thought experiment. And our goal is now to find how can we simplify further this phi, which is a function of 10 variables, 9 components of F and temperature. So let's see, think about this thought experiment now. So we have the reference configuration. So at time 0, we apply loads to the body, so it deforms, and for us that really means we have applied the deformation gradient F, and we are in the current configuration. Okay, like you start with the reference configuration, which may be stress free. We did not say anything about it. We did not say a single word about the stress state in the reference configuration. For the simplicity, we are going to assume that this body is made of one material. Every material particle in the body is made of the same material. So then it is a homogeneous body. Say homogeneous body is one for which every point in the body is made of the same material. It just is simplification, so I just have to I don't have to worry about saying, hey, you have this particle is made of copper and the other one is made of steel. Okay, so I apply F, which means I deform the body, and we get some stored energy, strain, like Helmholtz free energy phi. Now I rotate the body. So I take this, I rigidly, I know I cannot draw it, but I rigidly rotate the body. So let's say from here to there, I have rotated it, pure rotation. So you take the body, you deform it, you got F, now you rotate it. Rigid rotation, rigid body rotation. Even though I showed you translation also there, but we are talking about rigid body rotation. So will the free energy change? So 2 of you answered no. How many?
Can you repeat the question?
I'm sorry?
Repeat the question.
Okay, repeat the question. We start with the body in the reference configuration that is indicated in the blue color, and we are calling it omega 0. We apply loads to it, so it deforms. That we are indicating by applying F, the deformation gradient, and we get the red shape, or the shape shown in red color. So we find the Helmholtz free energy in that deformed state, red color. Now I rigidly rotate the body, red color body. Whatever loads were acting on it, or they are still acting, but I rigidly rotate the body. So will the Helmholtz free energy in the body shown in the black color be different from that shown in the red color? Okay, no. How many of you say no?
Yes. Yes.
Sir, then
Pardon me?
free energy should be independent of the coordinate axis, right? It is like rotation of axis.
Well, yes, it's a rotation of. I did not ask you for the reason. I just asked you, will it change or not change?
It will change.
How many of you say it should not change? It should be the same, both in the red color and the black color configurations. Free energy should be same. And what about the remaining? You saying it should be different? Why should it be different?
Because entropy will change.
I'm sorry?
Entropy will change.
Why will entropy change?
The position will, after rotation, position will change.
Did we say entropy depends upon the position? Did we say entropy depends upon the position? We said entropy depends upon the deformation gradient and temperature. So why should it change then? So roughly speaking, it's like this. You stand up, you have some mass. Then you rotate by 180 degrees. Will your mass change? You rotate by 70 degrees. Will it change? So that's the same thing here. So why, when we rotated the body, we did not do any extra work on it. We did not do any work on it. There is no deformation, there is no work required to deform the body. So the hypothesis is that the free energy should not change. This is one way of thinking, that you rigidly rotate the body. So this is called material objectivity, that our constitutive relation should be materially objective. Other possibilities, like you were saying, that you watch this experiment being done with respect to two different coordinate systems. Like I am in this lab, I have coordinate axes aligned along these three corners, and I apply this F, and I get this current configuration. But you are more adventurous and you are in a helicopter. Assume that this ceiling is not there, or it's a glass ceiling, you can see it. But your helicopter may be rotating with respect to my coordinate axis. So then you will see not this F, but you will see this F rotated by Q, a rotation, right? So will you see, what's your feeling now? Should the free energy be different from your observations of Q, deformation gradient, which is different from my observation of deformation gradient by a rotation Q? This should not be, it should be the same. Free energy should not change. Whether you are, because you are also, your deformation gradient and my deformation gradient are really differing only by rigid body rotation. And rigid body rotation should not cause any difference in the free energy. But the names associated with the two reasonings are different. So, one is objectivity, material objectivity, other is material frame indifference. Frame indifference means results should be independent of the frame of observation. And material objectivity means that if you superimpose a rigid body rotation, then you should not see any difference in the Helmholtz free energy. I did not say about stress tensor. I did not say a single word about stress tensor. Free energy is a scalar quantity. Temperature will not change, free energy will not change, entropy will not change. But the stress tensor depends upon the coordinate system, the components of the stress tensor. So, they will be different. Okay. So, now we need to translate that. So, if this is a rigid body rotation, let us say this is Q, or Q we use for heat flux, so that is not a great choice. So, what symbol should we use? O, orthogonal transformation. I mean, we have to use some symbol for this rotation. It's an orthogonal matrix. I don't want to use R because we used F equal to RU, polar decomposition theorem equal to VR. So, I don't want to use R. So I can use either O or Q, but again Q will be confusing because we just said Q was heat flux. So, that is not 0, this is an orthogonal matrix. So, if when I compute the free energy here, so I get phi of F theta, and if I compute it in the black configuration, what should I use? What is my total F in going from here to there? I am sorry? OF theta. So, I take whatever function you have, whether you plug in F or you plug in OF, you should get the same answer. Agreed? This is very important. Now you will see what happens. So, this phi F is RU, F is RU, polar decomposition theorem. Any 3 by 3 matrix can be written like that. Now, please listen. Now, is there any restriction on this O orthogonal matrix? Except for being an orthogonal matrix, is there any other restriction? No. So, I take O equal to R transpose. If R is orthogonal, R transpose is also orthogonal, and I take O equal to R transpose. It should hold because it holds for all O's. So, if I take O equal to R transpose, what will happen to this term? Identity. So, that means this should be a function of U. And U is symmetric. So, instead of having 9, now you have 6. See, instead of finding phi as a function of 10 variables, we have to find phi as a function of 7 variables. Temperature is not gone, I mean, it's still there. See, simplified the problem. I did not do any physical experiment. So, that is how far we can go with the theory. I mean, U, if you like U, you can write U as square root of C, because we said yesterday C is equal to U square. So, U is square root of C, so it is a different function of C. because this is square root, so I did not put the square root now. So this is a different function of E, because E equal to C minus 1 over 2. So I can substitute for C equal to 1 plus 2E, identity plus 2E. So now I think those of you who are asking me, yes, oh, quite new Hookean material, it will show up in a minute. So theory can go only this far, that phi must be a function of E and theta. What kind of function it is depends upon the material. So we have to do experiments in which we change one component of E at a time. It's a lot of work. There are 6 components. So we change one component at a time and find the expression for phi. Or you assume an expression for phi and then you will have fewer things to worry about. So if we are talking about anisotropic materials, we have not said, we are not assuming anything about isotropy, then this is the end. We have to find phi experimentally, or we expand now phi in terms of Taylor series. So let's do that. On the other hand, if I assume that the material is isotropic, then we can do some more thought experiments and simplify this a little more. So which one do you prefer to do now? Talk about anisotropic and or go to isotropic? Isotropic? Anisotropic. Okay. So anisotropic, so T IL, which we talked about, is then delta phi over delta FIL. That was required by the entropy inequality. That's what we got. So we can say this is equal to phi with respect to E mn, and you differentiate E mn with respect to F. Okay. So now let's see what. So I can erase this part. And let's see what is EMN. So what I'm really going to derive is an expression for the second Piola-Kirchhoff stress tensor. You will see that the expression for the second Piola-Kirchhoff stress tensor, actually I can give you the answer. This is going to be the second Piola-Kirchhoff stress tensor.
There should be a rho naught.
Oh, rho naught. Sorry, you are right. My mistake. But rho naught is mass density in the reference configuration, so it's not changing. So to make life simpler, let's say phi hat equals rho 0 phi. So that's the mass. Now it is Helmholtz free energy per unit volume rather than per unit mass. And if we do that, then I don't have to worry about this. So this is the derivative here. Because rho 0 is mass density, so it's not a function of F, right? So I don't have to differentiate rho 0 with respect to F. Okay, so let's first do this, and then you will see that indeed the second polar Kirchhoff stress tensor comes out to be this derivative. So EMN, I think we wrote, is 1/2 C, which is FIM minus delta Mn. And if we differentiate this, let me write J here. So because I'm going to differentiate with respect to FIL. So delta EMN over delta FIL. So that's 1/2. When you differentiate, now each one of these 9 quantities is independent. So J must equal I and M must equal L. Otherwise, you will get 0. This J must equal I and M must equal L. So if you differentiate F11 with respect to F12, you will get 0. So that means delta J I M L F J N plus F J M J I N L minus 0. So what is SLM in terms of the first polar Kirchhoff stress tensor? Oh, I think I had this more, I just used it, right? So we had Fs equal to T tilde. Should be IM, no, MI. So it's F inverse T. Am I right? Because we wrote Fs equal to that. I think that's what we wrote. Yeah, we wrote Fs equal to that. So it's F inverse. So now I have to be careful because I have Mn there, so I have Lm here. So let me change it to something else so that we don't M. Okay. So let's not use M here. Say P. That way, this P is not point, this is an index. So phi T hat tilde, so that's F IL. F inverse PI, and this one we are going to use this here. So that's delta phi hat Mn F inverse PI, and then Mn with respect to this, I copied that, and there's a 1/2 here, so I just copy that, delta J I delta ML FJN plus FJM JINL. I think I did okay. I did not think hard, but I just copied from here. I didn't copy 0. Is it okay? We will soon find out if how much What did I do? This is lowercase I. Okay. So this is equal to 1/2 delta phi hat over E m n I. So that will be J. F inverse F, identity. So this becomes identity. F in now I gives you J. F inverse F, identity. So what you get then is basically identity. That's LP. So you get twice delta L m delta P n. I showed you get identity plus identity. So that's two identities. So that's what I wrote, two identities. So this 2 cancels with that. The reason I just wrote that is because we are starting with LP, so we must end up with LP, and that's what I did. So what we are getting then is SLP equals delta phi hat over delta ELP. So phi, the Helmholtz free energy as a function of E, serves as a potential for the second Polar-Kirchhoff stress tensor. You don't like it? Is it okay? So the second Polar-Kirchhoff stress tensor, can be derived from the Helmholtz free energy by differentiating it with respect to E. Okay? Or the first Polar-Kirchhoff stress tensor can be derived by differentiating with respect to I, deformation gradient. But the Cauchy stress tensor does not have a potential like that. So the Helmholtz free energy serves as a potential for the first Polar-Kirchhoff stress tensor or the second Polar-Kirchhoff stress tensor, but not for the Cauchy stress tensor. So one reason people use second Polar-Kirchhoff stress tensor in codes is because of this relationship. Because phi hat serves as a potential. So you can write variational principle if you like, or principle of virtual work if you like. When we can write principle of virtual work in terms of the first Polar-Kirchhoff stress tensor too, but then you have to work with 9 components. Now you have to work with 6. S is symmetric. However, as I said yesterday 3-4 times, after you are done, you must find Cauchy stresses. So after you are done, you find S. From S, you find first Polar-Kirchhoff stress tensor. From first Polar-Kirchhoff stress tensor, you find Cauchy stress tensor. But since the deformation gradient is known, you have solved the problem. So you can find any component of stress tensor you like. But you must report your answer in terms of the Cauchy stresses. Otherwise, this second Polar-Kirchhoff stress tensor is mathematically convenient. That's all. It's mathematically convenient. It has no physical meaning. It has units of stress, which is, yes, that is true. Units of stress, yes, it has, because deformation gradient has no units. So units of T tilde and units of S are same. Just because units are same does not mean it has physical meaning. Just because something is in megapascals does not mean it it means something for the material. Many of us are goofed, but we get the false impression, hey, it has units of stress, so why is Ramesh saying it has no meaning? Because if this has meaning, this has when you are multiplying with this, you are multiplying with something like strain quantity. So it has lost its meaning, even though units have stayed the same. When you have multiplied by millimeter, but this F inverse has 9 components, and when you when you multiply, so the end result you will get is these components multiplied with those components. So it will have no physical meaning left. Okay, now, so the next step is, if I don't want to do physical experiments, then I will say my phi hat is a function of E and temperature. So I will expand this in terms of Taylor series 0, theta 0. So where theta 0 is the temperature in the reference configuration. E is 0 in the reference configuration. And I'm sorry, is there any question? Okay. Then the next term will be delta phi hat over delta E m n, evaluated in the reference configuration, and this is E m n plus delta phi hat over delta theta, again in the reference configuration, theta minus theta 0. This is free energy. We must keep second order. Now remember, when you will find S, you are going to take derivatives with respect to E. So if you stop here, you will not get stresses depending upon strains, because if you stop here and differentiate this with respect to E, so you will get this term, but that's evaluated in the reference configuration, right? That's what this symbol means, evaluate in the reference configuration. So you go further. So that the next one is del square phi hat over E m n E say A B and multiply with E m n. Again, this is in the reference configuration, E A B plus there is a factor of 1/2 excuse me, 0 theta minus theta hat 0 square plus 1/2 mixed term theta E m n theta minus theta 0 plus other terms. And there is no, I think there is no 1/2 here, because this term will appear twice. So there are 3 dots, so you can continue. So if I don't continue, I stop here. So I will get an approximation now. So if I stop, so that's an approximation. So as we were talking about this morning, that you have you have buckets of materials. So this is from that bucket you have taken a cup. So this bucket is full of thermoelastic materials. So you took a cup, and whatever came out in that cup, you took it out. So that cup is now full of these kind of materials. It's a subset of those thermoelastic materials. It's a subset because I did not consider the infinitely many terms there now. So it is a thermoelastic material, but it's not the most general one. Does it make sense? So roughly speaking, like you have a bucket full of, say, apples. Or maybe that's not a good example, because I don't know whether you get different color apples here or not. Because in the US you get apples, green color apples, yellow color apples, red color apples, those three colors. But here I don't know. Pardon me? Two colors. Oh, good. That will help. So red, besides red, what else? Green color. Okay. So you have a bucket full of green color and red color apples. So we have picked up now green color apples only. So this one does not represent all kinds of apples. And also you can say these apples were taken from the tree a week ago. Some things can be taken like 2 weeks ago. Their taste will be different. So depending upon how much you put in here, you will get a different material. But this is the simplest one can have. This is the simplest one, simplest nonlinear anisotropic material we can have. Actually, it's really not quite nonlinear. It's somebody used the word yesterday, New-Hookean. So this is a New-Hookean material. Hookean is for small deformations, and this one is for large deformations. But as you will see in a minute, stress strain law is linear, except that we are using different stress tensor and different strain tensor. So let me show you that part. So now there are so many of these constants. So let's say we denote these by Smn0. We denote this by eta 0. We denote this by CMNAB, and this one, I don't know, say eta 0, 0, and this one by alpha MN0. Because I don't want to write those derivatives again. Now remember, now all of these, they are evaluated in the reference configuration. So they are constants now for us, because they are evaluated in the reference configuration. You differentiate them and then set E equal to 0 and theta equal to theta 0. So they are not functions of E anymore. Does it make sense? Because we are expanding in terms of Taylor series around, we are expanding in terms of Taylor series around 0, theta 0. So once you differentiate and set E equal to 0 and theta equal to theta 0, this quantity is no longer a function of E. Same thing here, it's no longer a function of E. Am I making sense? So now let's differentiate. Let's use this.
Should that be eta hat not?
This one. If you prefer that, I can put hat on it. I mean, to me it doesn't matter, because it's a constant.
Because we have redefined the phi hat as rho naught.
Doesn't matter, because we are saying S0 is this quantity, right? So it doesn't matter whether I put hat on it or not. It's a notation now. It's a symbol. It has no, So I think it will be simpler not to put a hat, so I would have to write less. Otherwise, I will need to put hats on everything, and that.
In your last term,
Yeah.
that expression should Mn be outside that evaluation at 0?
Oh, yeah, yeah, yeah.
It is at evaluation.
No, you are right. You are right. My mistake. Yes, yes. You are absolutely right. Thank you. Yeah. Yes, yes. You are right. Yes. It should be. This is evaluated at 0, not this one. Yes, you are right. Otherwise, EMN is 0, the reference configuration. Yeah, I was too hasty. Sorry. Yeah.
Because we are using Taylor series expansion,
Right.
does it mean that my EMN has to be very small?
No. Why?
Because we have to take a small perturbation from the reference state, only then can we use Taylor series expansion.
No. No. Oh, no, no, no. It's not true. I mean, see, this is an approximation now. I'm not saying my Taylor series expansion is good, but I can truncate the Taylor series wherever I like and accept the error. So what is happening is I'm saying this is one class of materials. Like I told you, this is bucket. I took that cup. In that cup, I only consider materials for which phi is given by this. Now it's up to you. It's up to us when we do experiments and see that our predictions don't agree with experimental observations, then we can say one reason is because we truncated that series. Right? Other is, if you don't like to truncate it, do experiments and derive the expression for phi from test data. And that's a lot of work, because you have to vary 6 components of phi. And you have to vary them from 0 to maybe 5. It depends upon what kind of strains you are expecting. There is no limit on the amount of E we set. So if you have test data up to say from 0 to 5, then your predictions will be valid or should be valid for strains up to 5. But generally, strains of 5 is a large number, because most materials will fail before then, except possibly for rubber and possibly for my skin. So my skin is good. You see it? I mean, I can go 500%. And if you, for a newborn child, it's even more. You can go probably stretch even longer. Okay, so I think the answer to your question is, this is an approximation. This is a one class of materials now. If you don't like this, you can keep the next terms. And then you will get a different class of materials. And if you don't like that, you keep more terms or do experiments. There is no guarantee, there is no assurance that phi can be expanded in terms of Taylor series. There is no such assurance. Okay, there is no. I cannot guarantee you that for every material, every thermoelastic material, one can do something like this and you are okay. Because if you look at Fung's book, Y.C. Fung, he gives you stored energy functions, which are our phis here now, except temperature is kept constant. They are exponential form. But he is giving you for isotropic materials, which we have not talked yet. It will come, because you asked me to do anisotropic first. So again, those exponential functions, those functions derived are for a very limited, are based on a limited set of data. But we assume they are valid for a larger set. And as soon as you make the assumption they are valid for a larger set, your prediction may not agree with the experimental observation, because you derive the values of constants based on a limited set of data. So that's where the nonlinear elasticity becomes challenging, finding the constitutive relations. Even in this case, you will see that finding variables is not that easy. Physical meaning of this is going to be, this is the stress in the reference configuration. That's why I put 0 on top. This is the entropy in the reference configuration. This well, this is thermal expansion. So this one, MNAB, these are 6, these are 6. So you have 36, but these can commute. So you really have only 21. So these are 21 constants. Good luck in finding them from experimental data. So that's where the difficulty comes. Now, how do I find these 21 constants? I can't. It's difficult. And then this is for the second derivative, and this one is for thermal coefficients of expansions, because they are going to multiply these two terms. And when I differentiate, this will give you thermal stresses. So if you, I think I can complete, well, roughly you got the idea, because if you differentiate with respect to E, this is not going to contribute anything. So that's a baseline for free energy, which we can't find. We usually find changes in energy, changes in entropies, and so on. So this is not contributing to this stress part. That's a power of 1 power of E. You differentiate, this will be gone. So you will get stress S in the reference configuration. If you assume it is stress free, this is gone. Entropy. So that will give you change. When you differentiate with respect to theta, you will get entropy in the reference configuration. Again, we want to find changes in entropies. So if you, so in one way of thinking is these three terms are not contributing much. So you come to this one. So this one, we get S Lm equal to C Lm AB EAB. It's quadratic. You are differentiating once, so you get only 1 power of E is left. I did not give you the details in like differentiation yet, but when I differentiate, this 1/2 of factor will be gone too. So this one will give me temperature in theta, and that will determine my entropy as a function of theta. This one will give me coefficient of thermal expansion multiplied with elastic constants. So that will give me thermal stresses, because you are going to differentiate with respect to E. Okay, so you will get, if you are only interested in stresses, then you will get this plus, say, alpha m n 0 times theta minus theta 0. I'm sorry? Oh yeah, Lm. Yeah. You are right. Yeah, you are right. So now we need to find 21 of these and 6 of these. So if you are doing a purely mechanical problem, then you can forget about alpha Lm, say, like no temperature change. So we still have to find 21. And that we have assumed that the free energy can be expanded in terms of Taylor series. Otherwise, we have to find the free energy function. So that will give us a simplest nonlinear elastic material, or simplest material valid for finite deformations. So this one we can call neo-Hookean, because it behaves like a Hookean, looks like a Hookean. Stress is a linear function of strain. Well, sorry, you should not use the word linear because of this term. and if you don't consider temperature change, then stress is a linear function of E. And that's what Hooke's law says. So we call it neo-Hookean because it looks like Hookean, but now it is valid for finite deformation. But the second polar Kirchhoff stress tensor, whereas in the Hookean case, all stress tensors are same. For Hookean material, like linear elastic material, are small deformations. First polar Kirchhoff, second polar Kirchhoff, and the Cauchy stress tensor reduced to the same thing. And I have not shown you that, but basically you are taking my word for it at this time. Okay? So that closes the loop now. So for the mechanical problem we are done, because for the mechanical problem, in addition to the balance laws and the initial and boundary conditions, you need constitutive equation, and this is it. But we have to find 21 constants. Assuming you know them, then you can solve the problem. And I cannot tell you how to find these 21 constants because I don't know it. See, we have to figure out experiments that will give us these 21 constants. I can tell you for 2 or 3 or something like that, but or maybe 6. If I do orthotropic material, then there are 9. If we do transversely isotropic, there are 5. So if you do isotropic, there are only 2. So tomorrow I will show you that if you take an isotropic material and take different nonlinear relations, they are basically still A stress tensor is a linear function of A strain tensor, not the same ones, because we have to satisfy material objectivity that we talked about, and also if I take isotropic, then I have to satisfy material symmetry condition. So we will first start with how to define an isotropic material. Again, thought experiments. So think about thought experiment, how do we define an isotropic material, and then we will do that thought experiment and see what conditions it imposes on phi. And after you know what conditions it imposes on phi, life is simpler because you basically have to differentiate phi. Okay, so the exercise is think about how to define an isotropic material. Maybe I think it's 5 o'clock, so we leave. Okay, good. Thank you for listening, or at least being here.